Good morning, children. Today's class, first we will check the decimal representation of the following rational numbers which are mentioned on the board. The first rational number 20 by 5 with actual division 20 divided by 5. 5 fours are 20. Subtracting the remainder is 0. The second rational number 7 divided by 8 by actual division you are arranging as 7 as the dividend, 8 as the divisor. By checking the digit here you can see that 7 is not divisible by 8 or 8 0 is 0 7. You are placing decimal points and after decimal you can insert as many zeros. 8 8s are 64. You are subtracting 70 minus 64 is 60. Again you are bringing till you are getting a remainder 0. 8 7s are 56. You are subtracting 4. Again bringing 0. 8 5s are 40. Here you can see the decimal will have a proper place up. Each decimal will be placed in such a way that when you do an actual division, you will understand whether the division is completed or not. So 20 by 5, the quotient is 4 or can be written as 4.0. Decimal representation as 4.0. 7 by 8 is the same as 0.875. By logic, you can understand that 7 by 8 is a proper fraction. The numerator is smaller than the denominator. Definitely, it will be an answer in decimal. So, those children who are having a doubt of what's the difference between a fraction and a rational number, it will be clarified when you move into the third example. When you look into the rational number minus 36 by 6, you can see the numerator is minus 36 and the denominator is 6. Whereas here you can see both the numerator and denominator are only positive numbers, or in a fraction the numerator and denominator will be only whole numbers, whereas in a rational number the numerator and denominator can take any integer too. When you look into minus 36 by 6, by division, we will take only 36, ignore the symbol. The symbol can be placed after getting the quotient. 6 is our 36 and the answer is, remainder is 0. Here, by the law of integers, when a negative number is divided by a positive number, the quotient will take negative sign. Therefore, the answer is minus 6.0. These are the three examples. When you observe, the remainder has become 0 when you did the actual division. Let's take the example of the fourth rational number 18 by 5. 18 is the dividend, 5 is the divisor. As actual division, 5 3s are 15. 18 minus 15 is 3. You need to represent it as a decimal representation. So, you will place decimal and add as many zeros till the remainder is becoming 0. The first, immediately place the decimal on the quotient side also. You can bring down the 0 which makes the number 30. The dividend is 30 and the divisor is 5. 5 6s are 30. It is becoming 0. So the decimal representation of 18.5 is 3.6. What will be the decimal representation of minus 25 by minus 4? 25 divided by 4. 6 4s are 24. Then you are bringing 10. You are getting it as 4 2s are 8. 10 minus 8 is 2. And one more 0 and you will get it as 0. As the rule of integers, a negative number by a negative number, the answer will become positive, or it is plus 6.25. In all these examples, you can see that a rational number is divided. You got everywhere a terminating decimal. That means the remainder turned to be 0. Consider these examples. 10 by 3. 10 divided by 3. 3 3s are 9. 10 minus 9 is 1. The decimal representation. 3 3s are 9. 10 minus 9, again 10. 3 3s are 9. The decimal representation, you can see the decimal representation of 10 by 3 is not terminating, or it is not stopping, it is continuing. So the decimal representation of 10 by 3 is 3.333 etc., or you will write it as 3.3 recurring. The symbol you are using here is to be placed on the top of the digit which is recurring after the decimal place, not in the whole number part, in the decimal place. Question number 2, if you see 29 divided by 6. 6 4s are 24. 5, subtraction is 5. 50. 6 8s are 48. 20. 6 3s are 18. Again 20. 6 3s are 18. Again 20, and so on. Here you can see it is 4.8. The recurring digit is only 3. So to avoid it, you can write it as 4.83, which shows that only the digit 3 is recurring. 1 divided by 7. 1.0 divided by 7. As you know already that 1 is a smaller number than 7. That's why I already arranged as 1.0. 7 is divisible 0 times. You can avoid that step. 1 minus 0 is 1. Place the decimal exactly. 10. 7 1s are 7. 10 minus 7 is 3. The next digit 30. 7 4s are 28. Subtracting 20. 7 2s are 14. We are checking whether it is going to terminate or it is going to continue, or how far the digits are continuing. 7 2s are 14. 60. 7 8s are 56. Again, subtraction answer 4. Bring one more. 40. 1 2 3 4 5. 7 5s are 35, 50, 7 7s are 49. There comes the repetition of 1. It goes from here 1. It will continue as the same way as we have proceeded. Thus, 1 by 7 is equal to 0.142857. We know that 1 is going to repeat again. All the digits will recur again and again and again, which shows that you have to place the symbol on the top of all the digits 1, 4, 2, 8, 5, 7. Let me quickly explain how to find the square root of any number using long division method. By this division, you will understand what are irrational numbers. Find square root of 2 by long division method. When you are doing the long division method, you will arrange the whole number part, and the decimal part you will arrange with zeros arranged in double way. The first concept is, what's a perfect square close to 2? Is 1, 1s are 1, or it is very well the same as 1 square is equal to 1. The subtraction gives you 1. Decimal here. The difference in square root is you will bring 2 digits at a time. The next step is, what is the double of this quotient what you have got here? What is 1 into 2 is 2. You have to get a digit here in such a way that the units place, the digit has to be the same. With what number you are multiplying, the digits have to be the same. At the same time, it should be close to the value of 100. So by that you can see it is 24 into 4 is giving you 96. 96. 100 minus 96 is 4. As I told you, 2 digits will come down as 400. The double of 14, the double value of 14 is giving you as 28, and you have to insert a digit in such a way that the digits what you are taking has to be the same, as well as it is close to the number 400. You can get it as 41, it's only 281, 911. The same procedure follows. You will bring down 2 digits. Double of 141 is giving you, 282, and then you are providing a place in which a number close to 11,900. Let's check with 2,824 into 4. 11,296. You are going to proceed with 2 more zeros down and the double of 1.414, etc. When you continue this procedure, you can see the value of square root of 2 is 1.414, etc. Here, the division never stops, as well as none of the digits are recurring in a particular order. Such numbers which have decimal representation, which is neither terminating, non-recurring, they are termed as irrational numbers. So what are irrational numbers? Numbers which do not have terminating or recurring decimal. In short, irrational numbers are those numbers whose decimal representation is non-terminating, non-recurring. The very clear examples we take is square root 2, square root 3, square root 5, and the value of pi, which is 22/7, we often accept is only an approximate value, as the clear value of 22/7 pi or root 2 you can see in page number 13 of your textbook. Thus, irrational numbers are those numbers which have non-terminating, non-recurring decimal form. What is a real number system? A real number system includes the set of counting or natural numbers, whole numbers, integers, rational numbers and irrational numbers. The explanation from here is any rational number can be expressed as a terminating decimal or a non-terminating recurring decimal. But there are numbers of the form square root 2, square root 3, square root 5, the value of pi approximately, that is 22/7. Approximately, decimal representation is non-terminating, non-recurring. Such numbers are termed as irrational numbers. Based on the explanation given to you today, the first type of questions which can be asked: find the decimal form and write whether it has a terminating or non-terminating recurring decimal. The first type of questions which can be asked is just find the decimal form by actual division and mention whether it has a terminating or a non-terminating recurring decimal. You can try the questions from exercise 1.3, question 1. Please type 2. Convert the following into P by Q form. That means the decimal representation will be given and you will be asked to write as a rational number in the P by Q form. Here there are two methods of questions which will be asked: as a terminating decimal or a non-terminating recurring decimal. How do you present both of them in the form of P by Q? The terminating decimals 0.3, 1.5, 32.53. These are the first type of questions as terminating decimals, and the second type of questions as 0.5 recurring. That means only the digit 5 is recurring. 2.74, the digits 7.7 and 4 are recurring. 5.31 recurring. Here you can understand that only the digit 1 is repeating. Let's see how to work out one by one. Express in the P by Q form the first example of 0.3. It is a terminating decimal. It is very well can be connected with the way you have done the decimal, conversion of decimal into fractions. You will write the numerator as 3. As many decimals or as many digits after the decimal place you will write as per the multiples of 10. And any rational number, if possible, should be simplified or it should be expressed in the form, in the standard form. So here 3 by 10, which cannot be expressed or simplified. Hence, the P by Q form of 0.3 is 3 by 10. The second example of 1.15. So here after the decimal place you can see there are two places 1.15. You will arrange the numerator fully as 115. So the first P by Q form is 115 by 100. You have to reduce with 5. 5 2s are 10, 23 and 5 division with 5 it is 23 by 20. You can see here the simplification is over, or the P by Q form of 1.15 is 23 by 20. The similar way you can proceed when any number is given to you as 32.6 or 32.675. You can rearrange as the number of decimal places, the digits in the decimal places as division by 1000. The whole of the number should be arranged on top and you can simplify and express it in the P by Q form. The second pattern, or how to express a non-terminating repeating decimal into the form of P by Q. Let's take the simple example of 0.4 recurring. Here when you observe 0.4 recurring, which shows that only the digit 4 is recurring. Let us take it as x is equal to 0. Remove the recurring symbol, give the meaning as 4, 4, 4, 4, etc. The digit is not stopping, so please put etc. symbol. Here only one place 4 is repeating. If you multiply, since only one of the places is repeating, if you multiply both sides of this equation with 10, 10x is equal to, you can see multiplication by 10 means the decimal point will shift one place to the right. Once it gets shifted, you can read it as 4.4444, etc. Why are we doing it? We are doing it to make it very clear that after the decimal there should be only the recurring digits. Once again I will arrange 10x is equal to 4.444, etc. X is equal to 0.444, etc. When you subtract the equations, 10x minus 1x is giving you 9x. 4 minus 0 is 4. 4 minus 4, 0. 4 minus 4, 0. It will become simply 4. That is 9x is equal to 4, or x can be written as 4 by 9. Vice versa, if you divide 4 with 9, you will come into the same way as 0.4444, etc. This is the first pattern of converting any non-terminating recurring decimal in the form of P by Q. Let's see the second pattern as 1.2 recurring. The only difference is the whole number part here is 1 instead of 0. Decimal part contains 2. That means the digit 2 is recurring. The first arrangement is x is equal to 1 point, the digit 2 recurs. The same procedure. Once you see here only one place or only one digit is repeated, you just try to multiply it with 10. 10x is equal to, read this as together, 12.222, etc. Rearrange as 10x is equal to 12.222, etc. x is equal to 1.22 etc., which makes you very clear that after the decimal place only the recurring digit is placed. 10x minus x is 9x. 12 minus 1 is 11, or it takes the value 0 after decimal. Thus the P by Q form is x is equal to 11 by 9. Let's take another example with 2 digits recurring. 0.45. 0.45, both the digits 4 and 5 recurring. Arrange it as x is equal to 0.45, 45, 45, etc. Here, the multiplication of x with 10 or 100 or 1000 will depend upon the number of digits under the recurring symbol. Here there are 2 digits, which shows that the multiplication should be done with 100 so that the decimal place will shift 2 places to the right. If you multiply with 100, automatically it becomes 45.454545. Make sure that after the decimal only the digits, the recurring digits should be placed. Rearranging, 100x is equal to 45.4545 etc. X is equal to 0.4545 etc. By subtraction, 100x minus 1x is 99x is equal to 45 minus 0 is 45, 0, 0, etc. Or the value of x is 40. The next pattern you can see as 3.18, only 8 is recurring. See the difference here? 3.18, only the digit 8 is recurring. Our main aim is to arrange in such a way that after the decimal only the recurring digits should repeat. Let's write the first way as x is equal to 3.18888 etc. So the first multiplication will be with 10. The first multiplication is 10x is equal to 31.8888 etc. That will be useful for subtraction. Once again, with what you will multiply, so that again one more equation you will get with decimal point and the recurring digits to the right. Is multiplication, you are shifting this decimal place into 2 places. That means you are multiplying with 100. 100x is equal to, you can read it as together 318.888 etc. The rearrangement, by this rearrangement it will be easy for you to subtract with the bigger number on the top. 31.888 etc. 100x minus 10x is 90x. 318 minus 31 is 8 minus 1 7, and 31 it will become 287.00. X is equal to 287 by 90. The rules are: arrange x is equal to the same decimal representation with only recurring digits repeated. Multiply both sides of that equation x with 10, 100, 1000, etc. so that after the decimal only the recurring digits should be present. Subtract the equations, you will get the value of x in the P by Q form, and Express P by Q always in the standard